if we're looking at this as a surface and we're trying to figure out how I'm supposed to discuss the direction of the area, well, if we assume this is some kind of just pill-shaped surface, it has some kind of uniformity to it, but it's still, it's a surface, then the direction of the area changes at every point because there's a different tangent at every point. But we would still say the direction of the area is perpendicular to a plane tangent to that point. So if you can imagine a variety of planes all contacting the surface at a single point, the direction of the area would be considered perpendicular to the plane that is tangent to that surface. Now, there's something else involved here that might be a little bit more difficult to understand, but I'll do my best. For a single flat plane, like we talked about last week, one of the things that was not particularly difficult to understand was that, like the little whiteboard, there's two directions that we could draw that. There's two directions that we could use to indicate the direction of the area because it was a flat plane. So how do you determine whether it's going outward away from the plane or in the opposite direction of the plane? For a surface like this, you could make the same argument. But this surface is closed and bounded. I mean, the idea here is that this is a one smooth continuous surface. So it has been accepted that the direction of the area will always be away from the inside of the surface. It's been determined that it will always be away from the inside of the surface. Now, each one of these little places, I want you to imagine, is a very small swatch of area. A very small swatch of area. Is that word okay? Swatch, like piece of fabric. So if you buy swatches of fabric, they're small pieces of fabric. So these represent lots of very small pieces of the entire area. So each piece of area we would consider to be a portion of the entire area. The concept here is that I should be able to take any closed bounded surface, and if I add up all the pieces of the area, I should get the surface area of the shape. Now, I don't know that I would be able to do that, but if we were talking about a closed and bounded surface, in order to get the entire surface area, I would have to add up every piece of the entire surface. There's a symbology here that is going to be new to you. And it's not just the summation symbol. It's the fact that if we are meaning a closed and bounded surface, and we want to add up the entire area, then we put a little circle here inside our summation symbol. This means that you have to add it up over an entire closed and bounded surface. If I wanted to get the entire surface area, that's what I'd have to do. Now, dA has direction, so I should list this as a vector. But for a closed and bounded surface, the total area's direction will end up being 0, the direction. Because for every arrow in one direction, there'd have to be another arrow in another direction in order for it to be a closed and bounded surface. So the fact that the surface area has no direction is okay. The fact that a piece of area has direction is also okay. Does that make sense so far? Just trying to, I'm kind of baby stepping this because you're going to see what Gauss's law is in a moment, and I want to make sure that we've kind of covered this idea that area has direction. Now, part of the reason, go ahead.
So this is only true if the shape is symmetrical, right? So if we have like an asymmetrical shape, something would not get canceled.
No, even if it was asymmetrical, it wouldn't matter.
Okay.
It would still end up having a net direction of 0.
Okay.
Because the only way we can close the surface would be to make sure that every piece of area has a counterpiece somewhere to close and bound the area. Now, if you have a non-Euclidean surface, then that would not be true. But these would all, if we're talking about a closed, regular bound, three-dimensional surface, they would all equal out to 0. Now, here's where it's going to get a little bit more challenging, but you'll understand why this exists. What we're trying to do is we're trying to figure out how we can measure flux. I want to remind you that this is in service to a different idea. So why would we want to have a direction to our area? Well, remember when I was trying to describe how you skim the surface of a pool, and if you wanted the most amount of water to flow into the net, then you'd want to describe a way of how you tell somebody, well, this is the angle that you have to make with the water in order to get the most amount of water to flow through the net. Do you remember that argument we had earlier? Well, we're trying to find a definition, a way that we can define the direction of the area of the scoop. That's what this is about. It's in service to the idea of being able to describe to somebody what direction is a surface oriented. That's all this is. But for us, it's in service of the concept of flux. There are lots of different kinds of ways of describing flux. One of the more common ones, the ones that you guys probably know a little bit about, is energy flux. So the rays of light coming from the sun, all nice and uniform, parallel because the sun's so far away, and then they make it to the earth. So when we consider the earth and the way in which it interacts with those rays of light, it should be kind of clear to you that although the rays are all nice and lined up parallel, because the surface of the earth is slanting back further and further as we get towards the poles, the amount of energy flux incident on the surface isn't the same everywhere on the round earth. Wouldn't you agree that as you get towards the poles, there are fewer rays incident for the area in which it's supposed to be illuminated? If we're just to compare, this is the space between, this is the space between two rays here, and here's the space between two rays here. Is it clear that there's a lot more land getting the same two rays near the pole than there is near the equator? Well, that energy is what heats up the air and the ground. So since there's less energy per square meter near the poles, it's going to be colder near the poles. It's just a matter of how the energy works here. So you can kind of see even up here, right? A lot more area getting the same two rays of light. So we would argue that at the poles, there's a lot less light incident on that surface. Now, to describe this in terms of flux, in this case, this would be light or energy flux. And again, a flux tries to count how much of your thing is incident or passing through an area. So the energy flux near the equator is greater than the energy flux near the poles because there's more light per square meter at the equator than there is on the poles. Is that making sense so far?
Yes.
Now, mathematically, it's hard to describe to you exactly how you would come about calculating what flux looks like. But obviously, there has to be a way for us to categorize this, or at least a way to calculate flux. And a couple of things should be clear. It's probably going to have something to do with the area involved. right? I'm pretty sure the area is going to be involved. It's probably going to have to do with what field is passing through that area. But there's probably also going to have to be something that's related to the angle the field makes. Field makes. Well, that's terrible. Let's try English here. Angle the field makes with the area. All right, that's going to make a big difference. And that's kind of how the arrows there are working with the Earth. So we have to find a math that will do this. Luckily, fields are already vector quantities. And areas, I've now described as a vector as well. So to calculate flux, here's how we're going to do it. And this is how we're going to kind of agree to do it. Imagine I have just for this argument right now, that looks terrible. I need something better than that. So I want that. So I have some kind of square that I've turned in space. So if you guys imagine that this is some kind of square in space that's been turned sideways, and I have some kind of field impingent upon the square, with field lines passing through the square. So my square has, length and width. So this is that little board, right? Me just holding it up kind of at an angle. And I have some electric field, and I'm making a nice uniform field for right now. So we'll say this is our electric field that's passing through the space. Obviously, my electric field lines are somewhat at an angle relative to the board. So we could probably say that the board's area would be considered in this direction, while the electric field's direction is somewhat at an angle. All good? Well, is it clear that if I could align the electric field to be more aligned with the area, I would increase the flux? But if I continue to turn the electric field more away from the area, I would decrease the flux. I'd have fewer lines passing through my area. Does that make sense? So we're going to define flux as a simple product. The product of the electric field times the area times the cosine of the angle made between the electric field and the area. Cosine works. As cosine gets closer to 0, we get a maximum for cosine. As the angle goes to 0, cosine becomes a maximum. And as our angle goes closer to 90, we get a minimum for cosine. This is why we've defined area in the direction we have. And that also means that this can be written as what's called a dot product. Anybody who was in probably mechanics last year, we talked about dot products. But a dot product is a type of scalar product. And as vector products go, there's two different kinds of vector products. There's a vector product between two vectors that produces a scalar, and there's a vector product between two vectors that produces another vector. The dot product is the product of two vectors that produces a scalar. It tells you how much one vector is aligned with the other. That's what a dot product does. It tells you how much one vector is aligned with another. Vector products were different. They told you how much one vector was perpendicular to another. So like opening the door requires torque. We want the force to be perpendicular to the torque arm. So we used the sine function to describe that one. And the result was the rotation of the door. It had direction. So we needed our vector product to produce another vector. But the dot product tells us how much one vector is aligned with another. We had this for work. Work was a dot product. It was force dot displacement, both of these vectors. But what it told us was a quantity of energy being delivered to an object. And energy isn't a vector quantity, which should tell you flux is not a vector quantity. Flux is a scalar. It just tells you how much energy passed through an area. That energy could be an electric field, it could be light, it could be a magnetic field. Flux is just a way of measuring how much of something passes through an area. Now with that, symbols, I know. The dot product is just a bigger dot. You have to know that we're talking about the dot product because you guys have kind of worked it yourself a little bit and just drawing these little dots here to indicate that they're products is no big deal. But when we're dealing with the dot product, the truth is we're dealing with something that we take the magnitude of each vector and we multiply it by the cosine of the angle between them to get the true nature of the dot product. And we're going to like this. The symbol we use for flux is capital Phi. So it's like a I with a circle in the middle. That's the symbol for flux. Kind of like it because nobody knows what it is. Okay, so far, the symbol for flux. And the units, and this is important for us too, since we're dealing with an electric field, that's newtons per coulomb, and we're dealing with an area, so that's meters squared. So the unit for flux is newtons per coulomb meter squared. It's nothing pretty. It's kind of a pain. If you remember that a newton is got a lot of stuff inside it too, you'll realize that this is a very complex unit. Remember, the newton is kilogram meter per second squared. So when you really start to look at what this unit looks like, it's kind of a mess. Agreed? So it's hard to see in there, but this is kilograms meters cubed per second squared coulombs. Somehow that's our electric field flux. But it's important that you be able to break the units down all the way to their most complex form, because inside here are other units. And we're going to see that showing up here in just a few days. Okay, so I took all this time to try and carefully talk about flux, but let me just do something demonstrative for just a minute. With our width here and our length here. All okay? Has an area that's in this direction. Yeah.
So is that like, so this is what it looks like, and this is the area.
Yeah, so I'm just, same board, kind of sitting out here. You know, it's hard to draw depth like this.
Yeah, no.
So just imagine I've got. Okay. Flux is as much about the strength of the field and the size of the area as it is this angle. So if my field is like this, there'd be no flux because none of the field lines pass through the area, no matter how large the area is, no matter how strong the electric field is. And even just turning it a little bit, we still just get a small amount of flux. Flux is just as much related to this angle as it is related to the size of the field and the size of the area. It's important that you recognize you get maximum flux when the electric field is either perfectly aligned or perfectly unaligned, right? You get maximum negative flux here and maximum positive flux here. So flux can be positive or negative. So positive flux means the electric field is passing in one direction through your area, and negative flux means it's passing a different way through that area. That okay so far? All right, now I want to change this up a little bit. Imagine instead of this flat plane, that we place a solid sphere in this region of space. So three-dimensional sphere. I don't know how else to make it look like it's 3D, but I'm not going to try that hard, okay? So if it's a three-dimensional sphere in space, you can have field lines that pass into it on one side and then out of it on the other side, right? The field lines can go into that region of space and then pass out of that region of space. So consider if there's nothing emanating from inside the sphere, then if it's just in a region of space that has an electric field in it, it's probably experiencing zero flux. Because for every electric field line that passes into that sphere, there'll be a field line passing out of that sphere. Right? If it's just a closed sphere with nothing inside of it, then as field lines come in on one side, they create negative flux. And as they go out the other side, they would contribute to positive flux. The net flux would probably be zero. Right? We're talking about a closed bound surface where we had just field lines passing through space. Does that make sense? So go back to the ball, something like that. Right? I have a point charge here near a surface. I'll have field lines kind of strong and concentrated on this surface, right? The part where it's entering, but they're only going to enter from about here to here. That means, because if you look, and I saw some people make a face, if I draw a line, that's probably the best I can do, right? These field lines will just be grazing the surface. So in this section of the sphere, all the field lines are entering the sphere. But that means they all have to exit the sphere on this part of the surface. So although I might only have 3 field lines going into this concentrated area on one side, the same 3 are leaving on the other side over a much bigger area, which suggests that the negative flux from the left side and the positive flux from the right side should sum to give me 0. Situation we have no flux because no field lines are originating or terminating inside the sphere. Go ahead. Remember, flux is 2 parts. It's the size of the electric field and the size of the area. So as the electric field is getting weaker, we're spreading it out over a bigger area. And the net sum will still end up being 0. Same number of lines going in, same amount of electric field coming out. It's just that it comes in on a smaller area than it exits. Does that make sense? Now, the reason why I'm concentrating so much on these closed surfaces is because of what Gauss's law says. And here's where I really need to bring something together. Excuse me. Gauss's law is about flux. And I have to be very clear about this. It says the total charge enclosed in any closed and bounded surface, the total charge enclosed in any closed and bounded surface is equal to the net flux through that surface. Leave a space in front of that little symbol. I'll say it again. The total in charge closed in any bounded enclosed surface, it's got to be equal to the net flux through that surface. There is a proportionality constant that has to be here too to get the units to work out right, because this has to be in coulombs, and we already know flux is in Newton meter squared per coulombs. So this proportionality constant is important here. It converts our flux to how much charge must be there. There's going to be a few pieces to this I'm going to bring together, But the first thing I want to talk about is that constant. It has a name. It's called the permittivity constant. And what its value isn't that important right now. What it symbolizes is the permittivity constant represents how we believe electric fields can be established in the permeance of space. So there are very few universal constants that you've learned about. I think the only one you really have learned about is capital G as a universal constant. And we've added a few this year. We've added little e for the charge on the electron, but it's about electrons, and we believe electrons are everywhere, so that's a reasonable thing. Things like masses of electrons and protons are universal too. The permittivity, though, is something about free space. Just like with G, where we believe that the gravitational constant is the same everywhere in the universe, we believe the permittivity is the same everywhere in the universe. But this is the permittivity constant of free space, or a vacuum. There are materials that can change the permittivity. So, like wood has a different permittivity than air, and air has a different permittivity than a vacuum. So the permittivity is something that can be measured, and you can kind of manipulate it. So there are lots of materials that have a bigger permittivity than free space. But Gauss's law is dealing with, right now, free space. But if you were dealing with, say, the electric field inside a piece of wood, you'd probably use the permittivity of a piece of wood, because that would be the proportionality constant. Okay so far? But we'll just leave it as free space. What makes it a symbol for free space is that little zero that's there. Epsilon naught. And this symbol is epsilon. This is not the uppercase epsilon you've come to know for like summation. This is the lowercase epsilon. It's written several different ways. I have been trained to write it this way. So when we try and consider what it looks like, you know how much I love doing this. So it should be small like that, but it can also, in text, it's often written, like, I don't know, kind of a script or cursive E. So it really depends on which font you use for your book. I would encourage that you use just this symbol, because that's what it looks like on your equation sheet for the most part. And most Helvetica type fonts will look like this. But I've seen it in books looking like this too. So just don't be confused. It's what the permittivity represents, not so careful about what the symbol is. But it's lowercase and should be written smaller than the other symbols. All right. Gauss's law. So get rid of all this extra for just a minute and focus just on Gauss's law. Gauss's law is different than Coulomb's law. It is one of the first of what will be 4 Maxwell's equations. And although this isn't the final form that we're going to see it in, it is a good start for where I want to go. It states quite clearly that there is a relationship between charge and flux. And more than that, it's indicating about how the total flux in a region of space behaves and what's causing it, which is charge. This can be written a couple of different ways, but notice the inclusion of the letters INC to indicate that we're talking about charge enclosed in a surface. Since we already have some other symbols, we can write this in its expanded form to look like this. Now, I'm being a little bit more careful when I write this because there's pieces of this here that are important. And I'm bringing it together for the first time. We said that flux is equal to E times A using the dot product, but we also indicated that if we wanted to deal with a fully bounded surface, we would have to integrate over the entire pieces of area. So if we're dealing with a flux that is not the same over every piece of area, then we would have to find the electric field on every piece of area, take into account the angle between the electric field and that piece of area, and then sum up over all of the entire area of the surface. That's what all of those pieces mean. So I want to really go through that. This means each piece of area, how much electric field passes through it, so every swatch and how much electric field passes through it, the angle between them, summed up over the entire closed and bound surface.